Hey guys, I am going to go over what we talked about in class today. So I have this whiteboard app up so that you can see me writing. And since inequalities was the biggest thing you guys wanted to talk about, let's make that our focus. When you have an inequality, all it means is that they're not equal. So let's say we said 5 is greater than 2. 5 and 2 are not equal, which makes this an inequality. Now, since this is an inequality, we can talk about inequality symbols. This is the greater than symbol. We also have the less than symbol. And we have the equal to symbol, which I know is not an inequality, but you can combine it with other symbols to make new ones. For example, this symbol is the greater than symbol, and now it's the greater than or equal to symbol. This symbol is the less than symbol, and now it's the less than or equal to symbol. So what we are going to do is we are going to use our knowledge of inequalities to be able to solve them. If I am given an inequality, such as 3 is greater than 7 minus n. That means that my 3 over here is one side of my inequality, and my 7 minus n is the other side of my inequality. N is a variable, so it could be any number at all. We don't know what it is. It could be anything. Let's try some different things to see if we can make our inequality true. What if n was 10? I like the number 10. If n is equal to 10, that means we have 7 minus 10, which you heard in 2nd grade is impossible. You can't possibly do it. And you heard in 6th grade actually would just give you a negative number. And negative numbers are always going to be smaller than positive numbers. So if n was equal to 10, yeah, that would work. That would be true. What about 5 though? N was equal to 5. Well, if you're not sure, what you do is you take this number and you're going to plug it into the inequality. 3 is greater than 7 minus n, but now we're saying that n is equal to 5. So we take this n here and we replace it. 3 is greater than 7 minus 5. And then you keep going, just like you normally would. You solve. Let's do our subtraction. And you end up with 3 is greater than 7 minus 5 equals 2. 3 is greater than 2. Last time I checked, that was true. So we're all good. 3 is greater than 2, so yeah, n could be equal to 5. What about 4 though? If n's equal to 4, 7 minus 4 is 3. So that would be 3 is greater than 7 minus 4, which means 3 is greater than 3. But a number can't be greater than itself. If I have $5 and you have $5, you don't have more money than me. If I have $3 and you have $3, you don't have more money than me. We have the same amount of money, which means that this statement is false. This is a lie. This is a false statement. 3 is not bigger than 3. Which means that if n was equal to 4, it would not be true. What if n was equal to 0? 0 works. 7 minus 0 is 7. And last time I checked, 3 is not greater than 7. Which means that once again, we have a false statement. So we know that n can't be 4, and it can't be smaller than 4, but it can be 5, and it can be bigger than 5. So then here's what the question becomes. The question becomes, does that mean that n has to be 5 or more? Or does n just simply have to be bigger than the number 4? So we're going to have to try something in the middle here. Let's try 4.5. 7 minus 4.5 is equal to, well, I know 7 minus 5 would give me 2, minus another half would give me 2.5. And 2.5 is smaller than 3. 3 is greater than 2.5. So yeah, this number works, which means that any number bigger than 4 is going to work. The answer to this inequality is that n must be bigger than 4, and it cannot be equal to 4. That would be n is greater than or equal to 4. That is not true. N is greater than 4. That's it. But that's just one example. What happens if we have that greater than or equal to sign in the problem itself? Well, now it's a little bit different. Let's try a multiplication one this time. What if I said 6s is less than or equal to 24? Well, right off the bat, alarm bells should be going off in your head because you should know that 6 times 4 is equal to 24. That's a math fact. We know that. So s equals 4 should be something you want to try. We're going to figure out if that one is true or not. I think we all know that if we have 6 times 4, that equals 24, which means that it's also less than or equal to 24. What about if s was equal to 5? Let's try a number bigger than 4. Well, if s is equal to 5, we're going to have 6 times 5 is less than or equal to 24. Now hold on for a second. 6 times 5 is 30. Is 30 less than 24? Is 30 equal to 24? No. 30 is bigger than 24. So if 30 is bigger than 24, this is false. Does not work. Let's try a number smaller than 4 this time. This here is where our possible solutions are. We know s can equal 4. We know s can't equal 5. Let's try 3. Let's try a number smaller than 4. 6 times 3 is less than or equal to 24. And last time I checked, 6 times 3 was 18. That's true. 18 is less than 24. 18 is less than or equal to 24. So now we know that s could be 3 and s could be 4. And if you think about it, if s is 2, 6 times 2 is 12, 6 times 1 is 6, the numbers just keep getting smaller, which is always going to be smaller than 24. So if we're looking at a number line, we're trying to figure out where s is going to go on this number line, we know that s could be 4. We know that s could be 3. In fact, we know that s can be 4 and anything smaller than 4. That's just going to keep on making the number smaller and smaller than 24 when you multiply it by 6. But 5, we said, didn't work. And if we go any bigger than 4, we're going to get a number bigger than 24. 6 times 4 and 1 millionth is going to give you 24 and 6 millionths. So you're going to tip the scale too big over to the side of 24. And that's how that works. So we would say that 4 works for s, and anything less than 4 works for s. So s must be less than or equal to 4. And that's your final answer. Now I stuck this graph in here. Let's talk about graphing real quick. And yes, I did figure out the tool for the mass deletion. Oopsies. If I can get it to work right. One second, guys. There we go. Alright, let's talk number lines. If I've got a number line, it's going to have a bunch of numbers on it. But what numbers I'm going to put on it depend, what numbers I put on it depend on what the problem is. So you can start with the number line, and yes, this is extremely messy, and it is giving me a bit of a problem here. Because I can't use a ruler on my iPad, I am trying to draw this by hand. So I'm going to take a second and just really focus on making those lines neat. Because I don't want to be messy. I do have my time now. If I am looking at an inequality, now by this point, if you're graphing it, you've already solved the inequality. I gave you something crazy, and now you have a solution. Or I'm just giving you the solution, right? Let's say, pick a name, Steve. Steve has cats. He is allowed no more than 9 cats. So how many cats could he have? Well, Steve can have 9 cats. So the number of cats, C, could be 9. He could have 9 cats. He's allowed to have 9 cats. He just can't have more than 9 cats. He could also have 8, 7, 6, 5, 4, 3, 2, 1, or none, if he really wanted to. So he could have less than 9 cats. When you put these two symbols together, you have an equal sign and a less than sign, you get Steve can have less than or equal to 9 cats. That's what we need to put on this graph. We need to show that on a number line. So what I'm going to do is I'm going to put the 9, it doesn't really matter where it goes. Now we're not going to worry about negative cats in this scenario. That is a thing we can graph, but I'm going to show you how to show that you can't have negative cats at a different point in time in the future, okay? He can have 9 cats. If he can have that number, you're going to fill in that circle nice and dark. He can have less than 9 cats. You're going to shade in everything that is less than 9, including the arrow to show that it's going to keep going, okay? That's how you graph this. However, if you were going to graph something a little bit different, let's say it was a problem where Steve is not talking about cats anymore, he's talking about something else. Let's call it money. Let's use an M. His money has to be less than $9. He has to spend less than $9 at Dunkin' Donuts for some reason. For some reason, Steve can't spend $9 or more. He has to spend less than that. So once again, we're graphing our money. If you want to put less lines, that's fine. It's just a personal preference. What you really just need on there is that 9. That 9 is the one that matters. He is not allowed to spend all $9. Which means he can't spend $9, which means we need to put an open circle over the 9. But he can spend less than that. So we're going to shade in everything less than 9. And we're going to give that arrow a nice darkening to show that he can have less than that amount. He can't spend more than 9, so this amount over here is going to be left blank. If we had the opposite, if we had R is greater than 9, we would do the opposite. You're going to have 8, 9, 10. R needs to be bigger this time. Whatever your variable is needs to be bigger than 9. So we're going to put a circle around the 9. Shade in everything to the left. Nope, not to the left. To the left makes it smaller. To the right. And that shows greater than. Greater than a number, you put an open circle around that number, shade in everything to the right. Less than that number, you put an open circle around that number, shade in everything to the left. And if we ever have to change it, so it's an equal to, you're just going to fill in the number it could be equal to. And I'm going to leave that there. Happy learning, guys. We'll be around if you need us.